This video presents our work on Multi-Fidelity Policy Gradient, a control-variate approach that mixes scarce, high-fidelity data with abundant low-fidelity simulation data for sample-efficient reinforcement learning. Online RL is often bottlenecked by excessive interaction with the real world or a high-fidelity simulator. In many domains, gathering such high-fidelity data can be expensive, slow, or even unsafe, even though they're the most accurate. Some examples are autonomous driving, large-scale power systems, robotics, combustion, and molecular simulation. Meanwhile, many low-fidelity simulation tools have been developed, such as reduced order models, learned world models, heuristic rewards, or digital twins. These low-fidelity tools provide inexpensive ways to generate large datasets safely. However, the challenge is low-fidelity data are biased, so naively training on them can even hurt the performance in the high-fidelity target environment of interest. So we have a fundamental mismatch. High-fidelity data are accurate but scarce. Low-fidelity data are abundant but biased. The research question we look into is how can we enable sample-efficient RL in the real world by mixing multi-fidelity data while being robust to low-fidelity data biases? In other words, what's the right blender that uses low-fidelity data safely? We begin by modeling multi-fidelity environments as finite horizon Markov decision processes that share the same state action spaces, initial state distribution, discount factor, and horizon, but can have different transition kernels and reward functions. The learning objective is to learn a policy that performs well in the high-fidelity environment that we ultimately care about, i.e., maximizing the expected returns in the high-fidelity environment. In this work, we focus on the on-policy policy gradient setting. We maximize expected return using gradient ascent. The policy gradient can be written as an expectation over trajectories of a per-trajectory random variable x tau pi. Practically, on-policy algorithms sample trajectories from the environment and compute x tau pi from each trajectory. Algorithms like reinforce and PPO follow the same pipeline, but compute the random variable differently. Since there typically are multiple sources of randomness, to estimate the policy gradient accurately, on-policy algorithms typically need to sample many trajectories, average the computed random variable values, and take the gradient. The central challenge is that, in settings where high-fidelity samples are scarce, policy gradients must be estimated from a small number of trajectories. And the commonly used Monte Carlo estimator for the random variable mean suffers from high estimation variance and slow algorithm convergence. The strategy we take is to ground the learning in high-fidelity samples and use lots of low-fidelity data to reduce policy gradient estimation variance. Our contribution is MFPG, a multi-fidelity policy gradient framework based on the control variates technique. We sample a small number of correlated, paired trajectories from both high and low-fidelity environments, so their per-trajectory random variable values are correlated. Additionally, we collect large amounts of low-fidelity only trajectories to accurately estimate the mean of the low-fidelity random variable. MFPG then constructs a combined estimator by using a low-fidelity control variate term to correct the high-fidelity term. The rest of the procedure follows the standard on-policy policy gradient recipe: average over the scarce, paired data batch, take the gradient, update the policy, and iterate. In this paper, we instantiate MFPG with reinforce to establish a clean convergence analysis. On this slide is our combined control variate estimator, which we define as a new random variable z with c as a scalar coefficient. Choosing c to minimize the variance of z admits a closed-form optimum that depends on the Pearson correlation rho between the paired high and low-fidelity terms. In practice, we estimate c online from training data using running statistics. This estimator has two key properties. It is unbiased with respect to the high-fidelity random variable, so we do not bias the gradient. And its variance at the optimal c is reduced by a factor of 1 minus rho square. So higher correlation translates to lower variance. In the paper, we use this to prove faster finite sample convergence for MFPG reinforce compared to standard reinforce. So the bottom line is, better low-fidelity data quality translates to higher correlation, lower multi-fidelity estimator variance, and faster MFPG algorithm convergence. The last question left is, how do we draw correlated multi-fidelity samples? MFPG couples the two fidelities by controlling the randomness that the algorithm can control. Most importantly, the initial state and action sampling. When sampling the paired low-fidelity trajectories, MFPG resets the low-fidelity simulator to match the high-fidelity initial states. For action sampling, MFPG uses a reparameterization trick, draws a sequence of noise samples, and shares the same noise for multi-fidelity action sampling along the paired trajectories. We note that the sampled actions are typically not identical across fidelities, since the states can diverge due to the uncontrolled random sources. First, we show experimental results on variance reduction by MFPG. We first evaluate MFPG on the robot control benchmark Mu-Joko-Hopper task, where the high-fidelity environment differs by a friction change. The plot reports the empirical variance of the MFPG estimator for the per-trajectory random variable mean, shown as a percentage relative to the corresponding high-fidelity only baselines. When high-fidelity data are scarce, MFPG substantially reduces the estimator variance throughout the training. Our results in the paper suggest that this variance reduction by MFPG is far more substantial than the common single-fidelity variance reduction mechanism, such as state value baseline subtraction. Next, we evaluate how MFPG performs under different gaps between the multi-fidelity environments. We first test MFPG under different dynamics gaps, i.e., learning combining scarce high-fidelity data with abundant off-dynamics, low-fidelity data. Here we evaluate the Mu-Joko-Hopper task under gravity mismatch. The high-fidelity environment uses different gravitational forces, while the low-fidelity environment remains default. We compare MFPG against high-fidelity only, using the same amount of high-fidelity data. In mild to moderate dynamics shifts, MFPG consistently and significantly outperforms high-fidelity only. As the mismatch becomes extreme, the cross-fidelity correlation drops sharply, so MFPG's gains diminish and its performance stays close to the high-fidelity only baseline. The rightmost panel reports the estimated correlation coefficient between paired multi-fidelity samples. Consistent with our theory, MFPG improves when correlation is present because it uses that correlation for variance reduction. We next run baseline comparisons on Mu-Joko control tasks under a range of dynamics shifts. We compare MFPG against off-dynamics RL baselines, dark and par, and also a low-fidelity only baseline trained with 100 times low-fidelity data. All results are reported relative to a common high-fidelity only baseline that uses the same scarce high-fidelity budget. The main takeaway is that MFPG is the most consistent and robust method among the evaluated baselines across these shifts. This plot shows the Hopper task under different gravity shift levels. The y-axis is the performance difference relative to high-fidelity only, estimated via bootstrapping, so the zero line corresponds to high-fidelity only. Error bars show 95% bootstrap confidence intervals. Bars strictly above zero indicate a statistically significant improvement over high-fidelity only. In these settings, low-fidelity only does not significantly underperform high-fidelity only, suggesting the low-fidelity data are non-harmful here. MFPG is the only evaluated method that consistently improves over high-fidelity only across all settings. When low-fidelity data are harmful, illustrated by this extreme mismatch case, MFPG tracks the high-fidelity only baseline for most of training, while the other baselines fail catastrophically, demonstrating the strongest robustness of MFPG among the evaluated methods. The difference comes from design philosophy. MFPG grounds learning in high-fidelity data and uses low-fidelity data cautiously as a variance reduction tool, whereas off-dynamics RL baselines exploit low-fidelity data much more aggressively and can be misled under large mismatch. In the paper, we sweep 39 mismatch scenarios, and MFPG is the most robust among the evaluated methods, again consistent with the idea that MFPG is cautious. So far, we've talked about dynamics gaps. Next, we show a different kind of low-fidelity bias, reward misspecification. Here, the low-fidelity environment is not just inaccurate, it is adversarial and takes a negated reward function. We evaluate Mu-Joko-Hopper and compare MFPG against high-fidelity only, as well as a low-fidelity only baseline that uses 100 times more low-fidelity data. In the plot, low-fidelity only fails as expected because it optimizes the completely wrong objective, but MFPG still significantly outperforms high-fidelity only. The key reason is that even when the low-fidelity environment is substantially different, or even adversarial, MFPG can still benefit by leveraging correlation, including negative correlation between the multi-fidelity data. Let's wrap up with the main message. MFPG is a sample-efficient reinforcement learning framework that mixes scarce high-fidelity data with abundant low-fidelity simulation data. There are 4 key takeaways. First, MFPG is unbiased with respect to the high-fidelity data. Second, MFPG uses low-fidelity data to form a control variate and leverages cross-fidelity correlation for variance reduction. Third, MFPG handles both dynamics gaps and reward misspecification. Fourth, because low-fidelity data are used cautiously as a variance reduction tool, MFPG shows the strongest robustness to low-fidelity data biases compared with the strong off-dynamics baselines we evaluated. Future work includes a few directions. First, in Appendix G of the paper, we discuss extending MFPG to broader algorithms and settings, for example, to actor-critic methods, model-based RL, and more generally off-policy and offline RL variants. Second, a central driver of MFPG's gains is cross-fidelity correlation. So, an important direction is to actively enhance that correlation through better coupling strategies, better low-fidelity model design, or learned mappings that align the 2 fidelities. Third, we want to move to more general multi-fidelity settings, multiple fidelity levels, and cases where the state or action spaces differ across fidelities, which is common in real applications. And finally, we're interested in pushing toward real-world deployments, where high-fidelity interaction is truly scarce, and low-fidelity simulators are an essential part of the training pipeline. Thank you for watching. The authors are listed here. The QR code links to our project website with more details. We welcome questions and feedback.